My name is Sarah Uranowski. I head up all things product marketing for Energy Cap. I am your hostess with the mostest today, and very excited to hand you off to Tom Diliberti, who is our valued and trusted expert and is going to take you through BAS systems. But before I do that, housekeeping rules. This will be recorded. These are always recorded and should be available very shortly after we finish. We always send out that recording to you. So if you were either unable to attend this live or you know folks who would benefit from this, please go ahead and send that to them. And as always, we love interaction here at Energy Cap on these sessions. So please use the chat, use it liberally, ask questions. There's also a questions option or a questions panel, but feel free to use the chat as well. Drop in your questions as we go. I'm happy to raise them for Tom, and we'll answer those as we go. So again, feel free to ask away, ask all the questions. We want to be interactive. We want this to be useful for all of you. And with that, Tom, I'm happy to hand it to you.
Yeah, thank you, Sarah. Appreciate it. And thank you, everybody, for joining us today. I anticipate, because this is our sixth in a series, that a number of the people on the webinar today have joined us in the past. But for those who haven't, just briefly, I'm Tom. I've been working in the energy industry for more than 20 years and just a bunch of organizations around the country. My role with those organizations was always to try to help them to save money, try to reduce their energy footprint and just save them some money. And in the background is Energy Cap. It's the software that I used during that time, and it also happens to be my current employer. So we like to say good things about Energy Cap as well. But today, the topic is building automation systems. And so what I hope to do over the next hour or so is just take you through the architecture of these systems, talk about the set points. You'll see I've got a number of screenshots that I want to share today and talk about. So I do want to definitely invite you into a conversation about things you might see on the screen so that I can teach you as best I can. I certainly don't know everything, but because of these years in the industry, I've picked up a few things that I want to share. And like I many times do in these webinars, I want to end with the recommendations that I want to offer as strategies for you to try to save energy and help your organization become more efficient. Again, any newbies who are joining us today, you're jumping in midway through a roadmap. Back in December of last year, I did a webinar and I talked about, for organizations wanting to go through a shift over the course of a couple years of time, all the things that they could do. And so the first 5 webinars of this year have focused in the blue and the purple region that's part of this roadmap. And today you can see the little arrow there. We're focusing on the building automation. And this series will continue through the end of the year, and we're going to continue to talk about these topics. The overall vision we had here at Energy Cap was just try to provide information for our clients and anyone really interested to just go down this path and learn and find these strategies to try to find ways to improve. Sarah, if you may, I think we have a PDF of this particular document that we can drop in the chat too for anybody that might find it helpful.
I just dropped that in the chat for anyone who doesn't have it yet and would like it.
Awesome. So don't want to spend a lot of time here talking about the building automation architecture because there's a lot of information you can find out there, but I just wanted to give a cursory overview and then really focus a lot of my time on the settings within the system, the things that are typically sources of waste. And so I want to really focus on that. But to just set the stage and level set for people, this is how a building automation system works. And I'm referencing the picture over here on the right-hand side. Is that normally there's a user interface or a terminal, a computer that the people are worked behind. It's communicating with the building automation system, which has controllers, and ultimately those controllers out in the field are controlling devices. In the image here is of an air handling unit. So you want to think about your building automation system as the central nervous system to a building, but there's all these devices that are being controlled electronically, and at the end of the day, the building automation system is trying to keep people comfortable, and it's trying to manage your energy use and make sure the systems are running when they're supposed to and not when they're not supposed to. The other part of the lingo here, and this is the 4th bulleted point, is sometimes these systems are called BMS systems for building management systems or BAS systems, so building automation systems. I've even heard them referred to as just energy management systems. To me, again, it's a bunch of alphabet soup, and you can make arguments. There might be subtle differences, but the main theme here is it's an electronic system that's trying to control all the devices within your building. And this is, again, a simplified version of what's happening, just a high-level understanding. But using the graphic here to teach this idea is that, first of all, the system, the building automation system, has to take inputs. So it's sensing something out in the field. It might be sensing temperature or humidity or carbon dioxide. It's taking some type of input. And the second thing it does is it compares that input to a set point. So there's a set point that's identified by the user, and it's making the decision that it's either meeting that set point or it's not. So the third thing the system will do is it will check for errors. And so you have to identify a range of how far away from the set point you'll accept before you're quote unquote in error. And then the system has to adjust. So the fourth thing it does then is it takes that and it creates an output. So logically, the sequence is this. It takes an input, compares it to a set point. If it's an error, then the system will say, well, let's change the output. Let's change the flow of air, or let's change the temperature. Let's do something within the building in order to bring us back so that we have no errors, so that we're within range. The other thing that happens with these systems is they run continuously. And it's that last bulleted here. A typical controller scans inputs and updates the system every 1 to 10 seconds. But again, this is a user choice. So somebody at the end of the day is making the decision to make it every 1 second, every 5 seconds, every 10 seconds as these inputs are fed into the system. So what are these building automation systems controlling? Well, pretty much everything from HVAC to lighting, electrical, plumbing, and mechanical systems. The last two things, though, for many organizations, they could be part of a building automation system. So access and security could be part of a building automation system. But what I have seen many times is that's a separate system. So it's a system that runs parallel to your building automation system. And the same thing with energy metering. Again, could it? You're going to actually see in the screenshots today a number of energy metering or just electrical usage values that show up in the screenshots that I have, but it doesn't necessarily have to. Again, this is going to be unique by organization and by vendor. There are many different vendors that supply these systems. But in general, if you were asked the question, what do building automation systems control? Well, it's primarily HVAC and lighting. Another term that's used a lot is this idea of what's called a sequence of operation. So just reading this, because it's important to understand this very clearly, is that a sequence of operation is the written description for how a system should behave under different conditions. And so this, although it's a electronic system, it's a digital system, the user has to decide how that system is going to adjust or change. And so having these sequence of operations documented and in a location that you as the user can understand is really critical. And if you draw your attention to the bottom couple bullets here is that most building automation system problems stem from these sequences that never get written down. They never get programmed correctly. And here is why, just a little background on that. My experience in the industry has been that the building automation systems, as they're installed, as they're commissioned, and ultimately as they're implemented near the end of a project, the organization is rushed to get the project done. And so the people that are programming these systems are in a hurry, and they get a little loosey-goosey with documenting these sequences of operations. And so it's really important if you're new to this world that you start to hunt these things down and understand what the sequence of operations are supposed to be. I would equate these sequence of operations to the answer key for a test in your math class. In order for you to know if the system is doing what it's supposed to, you need to know what the answer key is. You need to know how you compare with what the behavior is supposed to be. So these sequence of operations, make sure you're looking for them, you identify them, and you're going to see once again in these screenshots that I share with you here in a second, that this particular organization that I took these screenshots from, they have a little link to the sequence of operation. And that's a great strategy for organizations to keep all the information in one spot so that you're able to hunt it down and understand if the system is behaving the way it's supposed to. So last couple of minutes, just want to give you that high-level overview for building automation systems, but this really is the carrot. This is the thing that I'm really wanting to focus on, is that up to 30% of energy waste in commercial buildings traces back to BAS faults and poor set points. And so if we know this across industry, that many people have the opportunity to save large sums of energy and ultimately large sums of money, let's go after it. So this is the most recoverable energy or most recoverable money that you can find without making a capital investment. But it starts with understanding what it's supposed to be comparing what it is, and then working towards adjusting it so that you can get the benefit from it. But 30%, so think about your organization, how much you spend in energy, potentially 30% of that is being wasted right now. So let's talk set points. I wanted to give you some of the most common set points, and you'll see these certainly in the screenshots that are coming up, and start to blend in some new terminology or some words that are really critical to your understanding for how these building automation systems function. So first, and maybe the most obvious thing is zone temperature set points. So heating and cooling set points, and I've given you a couple examples here of 68 degrees Fahrenheit for heating and 74 degrees Fahrenheit for cooling. Those are numbers that you'll see in a lot of systems and numbers that you should expect to see. The concept, though, of deadband is really important that you understand, and I want to take you through an example so you can appreciate how most systems operate. So let me take you through a day in the north in the wintertime when it's cold outside. A building might be coming off of a setback. So let's just say the inside temperature of a building is 65 degrees. So it's early in the morning, it's 5 o'clock in the morning, the system's turned on and it has to start to heat the building. And so in this case here, with this example, the heating set point might be 68 degrees Fahrenheit. And if it is 65 degrees to start, what's going to happen is the building will actively and aggressively heat to bring the building up to set point of 68 degrees. Let's suppose also in this scenario that the sun comes up above the horizon, occupants come in the building, heat loads start to grow. And so now the temperature in the building becomes 70 degrees or 72 degrees or 74 degrees. And it's not the heating system that's driving that change any longer. It's all the heat sources within the building. And let's suppose it gets up to 74 and even beyond 74 degrees. And now the building has the ability to cool. So its cooling set point is 74. And if the building gets up to 76 degrees, then the building is going to want to cool itself back down to 74. That long-winded explanation allows me to describe what the dead band is. The dead band is the range of temperatures between heating and cooling when the building is not actively heating or actively cooling. So it's a range of temperature, in this case, between 68 and 74, where again, the building is not actively heating or cooling. So it's dead to the systems. The systems will still be ventilating and they'll be introducing air in order to keep the occupants comfortable. But that's the concept of a dead band, and one that's applied across building automation systems in many ways, where there's a range of temperature or set points where nothing happens. The building just coasts. And maybe that's the best way of thinking about it, where the building is coasting rather than aggressively heating or cooling. So long explanation there on deadband. Other set points are supply air temperature set points. And I give you a range here, maybe between 55 and 65 degrees. Static pressure set point. Again, this is going to come up a lot over the next half hour as we talk about systems and the pressure. Chill water, hot water set points. And I flagged something else here, what's called a reset schedule. This reset schedule really is a critical idea for energy management. In theory or in concept, what the reset schedule is, it's a way for the building to adjust the chill water or hot water temperature to reflect the real need in the building, whether you're needing to heat a lot or cool a lot. And I've got some examples of that coming up as well. There's the CO2 set point. So again, this triggers ventilation systems to increase their flow or decrease their flow if you get out of set point range. And then it's the occupied and unoccupied schedules. And if you've been part of these webinars over the course of the last several months, you've heard me say this many times, but this is the single most impactful setting that an energy manager or somebody who's interested in finding waste, you've got to go after these schedules. It's just so common that people ignore these schedules, and there's huge opportunities. And so I just wanted to beat that drum again and make sure you remember, don't forget that as you digest this information.
Tom, we have a good question,
Yeah.
which I don't want to save to the end because I think it's a really juicy one. James says, Tom, value engineering is my worst enemy. Our team suggests best-in-class roadmaps for energy management, only to have them pulled later for cost savings. Any tips to help better sell these things to leadership?
Oh, it's a great question.
Hmm.
What I think you got to do, there's many layers to it, but one of the pieces of advice that I've tried to give people through the time is to try to conduct a pilot convince people as best you can to maybe invest money or to maybe resources is even a better description, to put resources around making change and do a pilot to show the impact that it can happen. Because if you can produce real world results of savings or reductions in energy, then people are more likely to listen. And so rather than trying to solve all the problems of your organization by, say, strategically trying to generate lots of capital revenue or trying to do something big, just take a bite of the apple. Just take a bite, show that it's possible, and then go back to people and celebrate your success. And that has been one way I've seen people break the logjam of just getting started. And again, we could probably unpack that for longer, but just off the cuff, I offer you that just as a nugget. So I wanted to give you a list here on this next screen here of what I'm calling the most common energy efficient set points. Would all of these fit in every circumstance? No. But I just wanted to draw your attention to some of these numbers. And as you review these screens that we're about to go through, I just want to make sure that these are the numbers that you begin to lock in on. So that occupied set points for heating and cooling, we mentioned those already, 68, 74. Unoccupied, 55 and 85. And you might be seeing those numbers and going, wow, those numbers are much broader than what I would expect. And what I would say with a word of caution is that your unoccupied set points need to reflect how your organization functions and also how your systems perform. And what I mean by that is I would not recommend low unoccupied set points for heating and cooling if your systems are, say, 40 years old and they're limping along and they're near the end of their life cycle. But if you have more robust systems that are able to recover and drive temperature change, then the way you're going to save a lot of energy is by having more aggressive setbacks. And so I offer these as two numbers to consider, but just you have to go back to your organization and your buildings. And even within your organization, you might find some buildings behave very well and perform very nicely with aggressive heating setbacks of 55. And then you have other buildings that just the best you can do is 65-degree setback. So I provide this range just to give you context, but it really is unique to the organization of the user. Mentioned a minute ago this idea of the dead band. And a lot of times these dead bands get squeezed down to 2 degrees. And I want to encourage you to keep them broader, like 4 to 6 degrees, because there's a lot of energy waste that happens when you squeeze the dead band, when you can simultaneously heat and cool. So a lot of waste associated with that. Supply air temperatures, when you're heating, many times you'll see heating supply air temperatures between 65 and 95 and even beyond that. But there's a pretty substantial range depending upon if a building is actively heating or whether it's just coasting along because the temperatures are already comfortable for people. And for cooling, many times you'll see a range between 55 and 65 degrees, and we'll unpack that a little bit more too as we talk about chillers and cooling systems. Static pressures can vary. The most common range is between 1 and 1.5 psi. Again, we'll show you that in some charts here in a second. Chill water between 45 and 55. Hot water supply. Want to teach you a little bit about this. Is the hot water supply for a building should vary depending upon how cold it is outside. And there's a formula in the industry, if you haven't seen this before, where what you need to do is you need to take 180 degrees and subtract the outside temperature, and that will tell you what your building loop temperature should be. So let me give you a scenario. So let's say you're in the north. I live in Michigan. So let's say it's a winter day in Michigan where the outside temperature is 30 degrees. The way most buildings are designed, if you have an outside temperature of 30 degrees, you take 180 minus the 30 and come up with 150. So 150 degrees is what the building loop temperature should be. Most of the systems are designed to take that 150-degree water, and there's enough heat in that in order to heat the building. But this rule, this 180 degrees minus the outside air temperature, is very common throughout the industry, and you should be aware of that as you're evaluating your building automation system just to see how the numbers check out. CO2 levels, if you were with us the last webinar, we talked about that quite a bit, but the most common range is between 900 and 1100 parts per million. Again, ambient CO2 is about 400, and usually when you get roughly 1,000 more than that, the space, they want you to ventilate more. So that's what you see in the sensors. And finally, the last set of numbers here deal with domestic hot water. So this is not the water that's heating the building. This is the water that's being used within the building. And so usually for hand washing in bathrooms and locker rooms, that type of thing, you'll see it's 120 degrees Fahrenheit. water that's supposed to flow into the kitchen for cleaning the dishes and pots and pans in the kitchen supposed to be set to 140 degrees per the health department. And then finally, the water that's going through the dishwasher is supposed to be set at 180 degrees Fahrenheit. Again, that's in general and what most health departments would advocate for and expect. And so just know that those are the common numbers, but I would always check in your region and make sure in your specific area that those are accurate. Okay, so let's make the jump now to taking a look at a number of different screenshots. And so let's start by talking schedules because this is where I always want to encourage you to start is these schedules. So what you see on your screen here is an example of what's called a weekly schedule. And so the green bars represent how the building is being scheduled Monday through Friday. You can see that very clearly shows up. The building on Sunday and Saturday is in an unoccupied mode. And many times, if it's not occupied by default, it'll go into the unoccupied mode. So if you notice in each of the days, Monday through Friday, where there's white and there's not the red of the unoccupied, it's also in the unoccupied mode. And so depending upon the system, they will allow you to either schedule occupied or unoccupied or both. But this is just what a typical system would look like. And this is where I really want to encourage you to start. The other thing that you have to understand is with these schedules is how they prioritize themselves. So how does the system take an occupied schedule and an unoccupied schedule if they are mistakenly put in the same spot? Because as people make mistakes and the system gets confused, somehow the system has to decide what the priorities are. And there's another tab here at the top of the screen. Hopefully you can see my mouse as I hover my mouse, this special events schedule. This special events schedule, and I've got a screenshot here in a second of that, but it's a way of scheduling events. And once again, the system has to prioritize. Is it going to listen to the weekly schedule first and foremost, or the special events schedule? And so understanding the priorities is really important to make sure that you're scheduling your system correctly. Another thing that I've seen a lot through the years that I wanted to bring to your attention is something that's called optimal start. Your building automation system might be designed in order to run an optimal start sequence in the morning. And what it's supposed to do, and just using this Monday here as an example, where the system appears to be turning on at 4:30 a.m., which means the system should start running at 4:30 a.m. Optimal start works backwards from when you want to go occupied, and it turns the systems on at the optimal time in order for the system to run with minimal use. Or to say that another way, it will turn the system on earlier on a severe weather day when it's really cold or really hot, and then it will make sure the system is at the right temperature when you get to the time that you're occupied. So it does the math backwards in order to turn itself on. I want to make sure if you have optimal start as part of your system, many times people don't schedule it correctly. If this particular occupied mode includes optimal start, what it means very likely the system would be turning on at 4 o'clock or 3:30 or even 3 o'clock in order to get up to temperature versus in the occupied mode where you want to be. Some people will interpret this that the systems turn themselves on at 4:30 rather than working backwards. And what I'm trying to stress here is you have to understand when your system is actually turning on, depending upon how it's sequenced, to make sure you're getting the results you want. Because once again, that's where a lot of waste occurs is at the beginning of the day if people are turning their systems on too early. This next screen here is just a high-level overview for what the schedules control. And many building automation systems, they use color. So pink regions and tan regions and red and yellow regions. Each one of these regions many times could have its own schedule associated with it, or these regions could all be bunched together in one schedule. And so with this theme of understanding your schedules, you really have to understand when you schedule something to turn on at a certain time and then turn off, is it turning on all of the colored regions in this particular space? Is it only turning on, say, this pink one up here at the top? You have to really assemble all the pieces in your mind and take screenshots of this and talk to people and confirm in the field that things are actually turning on the way you would expect. Again, a really critical part of carving out that waste. And finally, regarding schedules, this is an example of those special event schedules. So what this menu allows you to do is it allows you to take the different months of the year and identify dates that you might want to operate your building in a different way. So if you notice here, the dates that are being flagged here on this exception schedule or event schedule, these are holidays. So these are dates that are unique where you might want to remain in an unoccupied mode. So the way most building automation systems work is you set up these special events. You can turn things off, set them in an unoccupied mode, or run them differently because it makes sense to do so. And the way most systems work is they will take and special event schedules will override weekly schedules. So you don't have to change your weekly schedule. These special event schedules will then dictate how the building will run during those unique periods of time.
We had a comment about schedules, which I think is also a good point, that Chris uses them to avoid peak time startup, which avoids obviously the cost associated with that.
Absolutely. It's a critical part. And Sarah, for the people out there that are beginning to get to that next level of understanding and understanding peak loads, one of the things that I want to help people understand is looking at peak loads and startup is certainly very important, but the rules change depending upon the systems you have. If a lot of your air handling units and systems start with what's called soft start, or they have variable frequency drives, things that don't spike energy use at the beginning, then you have to be a little bit less worried than you do if you have all sorts of systems that slam on first thing in the morning. But Sarah, to your point, and ultimately the person who made the comment, it's very important you understand both your systems and what's happening and look at the loads to make sure you're not creating waste or just really in that case, it's not so much waste as much as it is you're losing money because you're paying more than you need to.
James says they get an extra 1 to 2 days of extra energy savings by using schedules to keep their buildings in an occupied setting for all holidays that fall over a weekend and advertise it as holiday hibernation, which is really fun.
Yeah, that's awesome. Every organization has its own culture and people are at varying degrees willing to change or to adjust. But I think having positive message and finding ways to communicate with people and keeping it really optimistic and no better word than positive, people respond, and so if you want to spin it as hibernating, then hibernate away and help your organization save some energy.
Yep.
Yeah. So want to switch to another gear here of more screenshots. And if you notice here, this is the first one that looks like this has kind of got the green background. I've using these purple boxes to flag some of the things that I'd like to comment on. But please, if there's other things that show up on the screen that I can help you to understand, let me know. But just starting here on the left, one of the things in this particular system, when I took the screenshot of this, it's important to note that the outside air temperature was very mild. It was a very mild day in here in Michigan. And that's important because it allows you to look at things like this hot water supply temperature and hot water return temperature and understand what should be happening. On a mild day, the water that's going out to the building and the water that's returning, there should not be much of a temperature difference here or a delta T. And what's interesting about this is the hot water going out is actually coming back warmer than when it's returning. Okay, so it's the water going out is cooler, I should say, than when it's returning. It's warmer. So this is unusual. This might suggest that there's one of these sensors is reading a little bit wonky. Nothing crazy here, but look at these hot water temperatures to make sure it makes sense with what the conditions are in your building. Likewise, these chill water temperatures over here. So chill water supply, so cold water going out to the building at 46 and it's returning at 48. And so it's warming up. So this is picking up a little bit of heat as it goes around. And this right here, condenser supply and return, suggests that you have a cooling tower. And so as you learn your systems and understand what these set points all mean, there are little indicators here to understand what you've got out in the field. Another thing that I wanted to use this slide for is this idea of a supply fan command, and a supply fan status. So these two different descriptors are very common with building automation systems, command points and status points. So what this is saying is this supply fan is being commanded on. So the system is saying, fan, you need to run. And this point here, the status point, is telling you what it's actually doing. When these two things differ is when you have a problem. But these two things should always be in sync, and it helps you understand better what's happening downstream. Let me take you to the next one. A couple of things I wanted to talk about here. Mentioned in the previous slide about just the hot water supply temperature, hot water return temperature. This represents a system that's actually heating, right? The supply temperature going out at 149, it's coming back 131. It means that there is heat being lost in the system. And when I say lost, it's being used by the system, hopefully for the right purpose of heating the building. It's a little bit surprising because of the mild temperatures in this particular day, but that's what this is telling you here when you look at these particular numbers. I also want to introduce a new idea that I haven't mentioned yet, this idea of what's called an enable temperature or an enable set point. So what this is saying, because this is a hot water system, is anytime the outside air temperature is less than 85 degrees, this system is going to work. So the heat would be available to run in this particular building. And you'll hear me come back to this in another couple of examples here. Another thing in this slide, these heating coils, this is very common in building automation systems where they'll take these heating coils and they'll put them all on one screen and they'll color code them. So you can see if spaces are cold or spaces are warm. Just gives you a chance at a glance to see how your spaces are performing. Again, the color coding here helps just with a visual identification. And one other thing in this screen I just want to point out is I didn't mention early on in the webinar today about how building automation systems can measure power, electrical loads, and this peak demand here is coming in. So that value is being fed into the system here. And so if you're trying to track your peak demand or see what's happening, your building automation is giving you some information here as you're trying to relate this back to your bill. So just look for it. Many times it's there on the screen, might be hard to find. Sarah, I see you popped in again. Did you have another comment or question come up?
We've had a couple, but Tom, I think they're good general questions. We'll save them for the end.
Okay, awesome. Okay, jumping out of the next thing here. So I wanted to point out on this particular slide something that's a little bit unique here, this air handler one. And this is one where I would say is a little bit of a head scratcher, where if this were my building, I'd want to understand it a little better for a few different reasons. So for this air handling unit, this discharge air temperature, what this is saying is the temperature going into the space is roughly 58 degrees. Well, for this type of air handling unit system where it has mixed air, there's going to be a hot duct and a cold duct that come together to mix the air. And so if this mixed air temperature is 78 degrees, it's a little bit surprising that the discharge air temperature would be so dramatically different. So this might be a sensor issue. It's just an inconsistency with how I'm viewing this. And also the return temperature coming from a couple different spaces for this air handling unit, pretty comparable, which means the air coming back. This represents for many organizations, actual temperature in the space is about 74 degrees. Okay, so again, something might be a little bit weird happening here, but this is giving a nice consistent 74 degrees is coming back from the space. And another thing I wanted to point out here in this purple bubble is this idea of the supply fan. Whenever you have VFDs, variable frequency drives, so these are motors that can spin at different speeds, they're designed to not necessarily have to run at 100%, and that's the point. The point is when motors run at less than 100%, they save a lot of energy. And for both of these VFDs to be running at 100%, it's a little bit suspicious based on the time of the day I did this analysis. And also the static pressure being 2.6 is very high for many systems. And so there's a lot of things to unpack here. Again, if I was an energy manager in this particular environment, I would spend some time understanding this unit and these systems and finding out what's going on here, because things are just, it doesn't feel right to me. And that's really what I'm trying to do through this whole webinar, is just help you to understand when things aren't right so you can spend some more time looking at it. And finally, on this screen, this idea, this system reset or this little dial here, this I wanted to bring to your attention because I've seen more and more organizations begin to program this into their system where there's a master reset button, or there's a button that would allow the organization to very quickly change something significant. The best example I can come up with, in the years I've worked with a lot of school districts, and school districts in the north will have snow days. And whenever there's a snow day, there's a great opportunity to save a lot of energy because there won't be occupants in the buildings. And I've encouraged school districts to program in a button similar to this. It wouldn't be, auto and reset. It would be essentially a scheduling button, but it would be the same type of master control that would allow you to put all buildings in a school district or all the appropriate ones into a setback mode. So you're not heating buildings that have a snow day. So that's what I wanted to point out here again is don't disregard a master button. If there's a way that your organization can use some type of major control, think about it, program it in, talk to the people in order to execute that. Another screen here, wanted to point out a couple things with this, and I'm going to flag on this example, this idea of a cooling enable set point and then heating enable and disable set points. So let me take you through a scenario here. Let me take you through one similar to what I had given you earlier, where it's a colder day that gets warmer. What this does is when you see these values here, this is saying when the temperature is less than 50 degrees, the heating system is going to be enabled. So it means you're going to have access to hot water and heat in the building. As the outside temperature gets above 50, at 51, what's happening is you're between the enable and the disable set point. So the system's kind of coasting. But when you get over 52 degrees, now what it's saying is the system is going to turn itself off. So it's not going to allow the system to heat any longer. The logic being it's so warm outside, you don't need heat any longer. And as the temperature rises, you slide over here to this side. Now the cooling system is going to start up at 57 degrees. So we've created a temperature band between 52 and 57. It's this idea of a dead band again, where the system is not going to actively heat or cool. It's simply going to coast along. And this is a great strategy for energy conservation, is to create this band of temperatures where your building can't heat and it can't cool because it's so mild outside. And this is going to be unique by building and by system, but this is something that you should definitely be aware of and understand in your buildings, is when they enable and when they disable. All right, I want to take you back to this idea of a reset schedule. I mentioned this earlier on, and this is an example of a reset schedule, and this is how to interpret this. In this system here, when the outside air temperature is at 20 degrees, it's saying the hot water supply temperature is going to be 180. Also, it's saying when it's 55 degrees outside, it's going to be 180. This, folks, does not represent a reset schedule at all. This represents a situation where, for whatever reason, this organization is saying, we want the water temperature to always be 180 degrees. And in some cases, that may make sense, but usually it does not make sense to keep this. You want to follow this rule that I introduced earlier. It's 180 degrees minus the outside air temperature would give you the loop temperature. And this is saying that it's always going to be 180 degrees. So this is a huge opportunity for savings. So if any of you encounter this, I would take a look at that. And this is what you're going to want to see. This next slide is an example of one that's set better. What this is saying is when the outside air temperature is 25, I should say, the hot water supply is 180. But when the outside temperature is 60, now this is programmed to become 150. So what that means is that the outside air, as it rises from 25 to 60 degrees, again, outside, it's going to allow the loop temperature to decrease from 180 down to 150. This adjustment in temperature is a huge energy savings opportunity for an organization. So if you are not making use of reset schedules, please take a look at that. And another way of saying this is this, if you always have the water at 180 degrees during the mild time of the year, so the spring and the fall, you are creating an awful lot of heat that is wasted. This whole concept of a reset schedule is in order to allow you to take advantage of times when there's not the heating demand need. And so again, take advantage of this. I circled these pumps here to highlight this, is that many times, and it's even shown in the picture here, where these pumps, I would describe this as redundant pumping. There are two pumps here because if one fails, you don't lose the system. So these two pumps are in a position, the piping, it could go up or it could go down in order to get out to the building. The energy event here, though, is you want to make sure that only one of them is scheduled on and the other one is scheduled off. If both of these are scheduled on, it provokes the question, why? Sometimes when it gets really cold, people want to turn both of these pumps on. But in most situations, systems are designed to run either one pump or the other, and running them both redundantly is energy waste. So keep your eye out for redundant pumping and make sure it's being programmed correctly. Okay, let's see. So we're switching gears on you now, talking about a cooling plant. So moving from boilers to chillers. So here you've got a cooling tower. Some examples of a cooling tower. Again, I have a VFD that's running at 100%. This is a mild day. It seems illogical to me why it's running at 100%. That would be a red flag for me if I'm managing this building. I'd want to go check it out, see what's going on. We've got another enable set point up here of 56 degrees, which means that when we get above 56 degrees, the whole cooling plant is going to operate. And I also wanted to bring to your attention this idea of the pump rotate, this little purple box here. This is saying that these pumps now, these redundant pumps, this is another example of one. Again, one's on, one's off, which is good. But what this does is it tries to keep both pumps running for roughly the same amount of time. And saying that a different way, this pump might run for 24 hours and then this pump run for the next 24 hours. And they'll alternate back and forth because strategically, what you want to do is get equal wear and tear in these pumps because it's cheaper when you replace one pump to replace both pumps at the same time, get the contractor out there one time to do it. And so what you want to do is you want to have equal wear and tear. And so you see this in the system as well, where you want to rotate or make sure that these, the life cycle of these, they run in parallel. Okay, this slide talking about air handling units. I just wanted to bring to your attention these unoccupied set points. Again, just as an example, they're in the system, they're programmed in at 60 and 82. Also wanted to bring to your attention this idea of, you've probably noticed in many of these screens, there was a button for a sequence of operations. This is just the first time I happened to flag it. But this button in this system allows the user to go in and actually see how this particular unit is programmed. Love that idea. Love keeping the documents and all the logic available for people to look at. And then talking through the system here a little bit. This is an air handling unit. So what's happening here is the air is coming in from this outside damper. So it's set at 10%. So air is coming in this situation. It's going across the fan. It's being split into a hot deck and a cold deck. It's going to be recycled. So the air that's returning here, it could be ejected from the building, just exhausted out of the building, or it could be recycled. So the air flow through the system. But I wanted to highlight this idea of the minimum damper set point. This is a very common programming decision that people make is they set their dampers in a minimum position. And so 10% is very common. It's certainly not wrong, but I want you to be understanding what that means. It means no matter what's happening in the building, as soon as this system turns on, this damper is going to 10%. And if there's no occupants in the building or very few occupants, it means that you're heating or cooling air that you don't have to because you're in some type of minimum position. And so this minimum damper position, again, is something that some organizations want because they're concerned about ventilation. They set it at 25% or they'll set it at 30%. This has the potential for being a big energy waste again. And so you want to understand how this is set, what the rationale is, and the logic, both programming logic as well as the people that are making these decisions in order to make sure that your systems are set in an efficient way. A couple other things in this screen that are new, this idea of a static pressure set point. So here it's giving you this set point. So this is the command, this is the status. Notice these things are very close, almost 1 and 1. So that says the system is working the way it's supposed to. So that we haven't really seen that before. And this is unique too on this one here. They have an economizer changeover set point. So an economizer, I mentioned this in our webinar the last time, is economizers are a damper control strategy to suck in more outside air when the outside air is good. It's the right temperature, it's the right humidity level, and you want to get free cooling from outside and not have to manufacture cooling. So this economizer set point is the temperature when the dampers are going to start to take control. So they will open or close depending upon what the conditions are outside. My main point with this, not so much the temperature as much as is your organization using this? Because a very common phenomena, I've seen people disable this, or they'll have it set to a number that doesn't make any sense because they don't really know what's going on. Economizers are a great energy conservation tool, but if they're disabled or not used, then you've lost that ability. So that's what I'm trying to flag by that particular box. This one here is an example of a screen where things start to light up different colors because the controller's offline. So as you're scrubbing your system and looking for opportunities, try to find these things and bring attention to this because these are the things that very likely this unit is, it's one of two things. It's probably running all the time, or the other possibility is many times these controllers, if they go offline, they will run the last schedule that was programmed into it. Again, that's a decision that somebody had to make. So you want to find out if your controllers go offline, what's going to happen, but look for these in the system. Most building automation systems will flag this in a way similar to what's seen here. Okay, chunking along to this next one, this dedicated outdoor air system, this BAS unit. What I want you to see here is these dedicated outdoor air systems are bringing in outdoor air. So it's coming in through a damper position and it's looking at the outdoor air temperature. So it's pulling it in. It might be heating or cooling it. It's shooting into the building. But the takeaways with these BAS units is they should be producing what we call neutral air into the space. These systems are intended to temper the air, to maybe heat it up a little bit or cool it down a little bit or dehumidify it. But the idea here is not to aggressively heat or cool, it's to temper. And the other thing, and why I put this in the purple box here, is these systems always have to be tied back to an exhaust fan. Because if you're bringing in a bunch of air into a space, you can overpressurize the space if you don't have a fan to remove air from the space. And so you want to make sure that this is programmed correctly and make sure that when you're looking at building pressure or you're taking a look at these set points, everything seems to make sense. And again, just highlighting the most important thing, these BAS units have to be connected to an exhaust fan. So we need to make sure the programming is right in order to keep the building pressure right. Taking a look at this unit level page. This is, I just thought a nice little screenshot of a couple rooftop units. So it's looking at static pressure. And one of the things that's a little bit inconsistent here is some of these values here, this set point, these are extraordinarily low. These don't really match, and the static pressure is much greater. And so this is another one of those energy opportunities. And this may or may not involve over energy usage. The biggest thing is there's inconsistency here that I would flag that would be brought to my attention. And I would try to figure out what's going on here because these numbers, again, don't match these other values. This summary page, wanted to bring to your attention here. If you notice these supply fan speeds, I'd mentioned how these VFDs, when they're at 100%, you're not taking advantage of the opportunity to save energy. So what I'm seeing here is every single one of these supply fans is running at 100%, and this is for an energy recovery unit. This is just very unusual. Sometimes what this means is people have given up on the energy recovery units and they just program them in a simple way. And along the same line, one of the things that's confusing when looking at building automation systems is programming can happen at a couple different levels. You can have programming in the building automation system, but these variable frequency drives that are running at 100% have their own programming. And so sometimes there's conflict between the device in the field and the building automation system. And so I can't say 100%. I don't know whether there's a problem with the building automation system or something actually in the field. All I'm saying is this is something that's worth highlighting and tracking down because it is not intended to be that way. The whole point of having the fans, once again, is to run at speeds less than 100%. This page here, and I think this is I've only got a couple more of these, and then we're going to kind of begin to summarize. I know we've got about 10 minutes left in the webinar, but what you see here is a summary page of all of these units with airflow. So the CFM is cubic feet per minute, And why I've brought this to your attention here is whenever you have VAV boxes, or what are called terminal units, that's what the TU stands for over here. What it is these get programmed with a minimum and a maximum airflow. So this here, when you have restrooms with the same number, both as a minimum and a maximum, that's not normal. This was not designed to be the same. This is more typical, this coffee workroom where you have a maximum and a minimum flow that's different. And if you read down this list, again, you might find some consistencies, some inconsistencies, but the main teaching point in this particular screen, all of these things are part of the MEP documents when you get a building. What I would strongly recommend you do if you have sophisticated systems like this is you have to compare these values that are programmed into your system with the values for how the system was designed to operate. You'll see it in a table or a chart. These values were designed by the designer of the building to run at certain levels. But this is the number one thing that I see changed by people in the field when there are occupants that are uncomfortable. They will change these airflow settings because they want to make a little more airflow in there. They want to make it a little bit hotter. They want to make it a little bit colder. They want to reduce these things. And in the process, it gets the system all out of whack. So the main takeaway on this is if you have sophisticated VAV systems with terminal units or VAVs, you have to go back to the answer key, to the MEP documents, and find out how it was designed and how it's supposed to be operated, because very likely your system is not running the way it was supposed to be operated. Okay. All right. So the last screenshot like this before I begin to summarize is I wanted to show you this. This is an electrical, just some feedback that you can see in the building automation system. And if you weren't aware of this, is whenever you have three-phase usage of electricity in your buildings, these values need to be close to the same. So at a glance, when you see these values all around 283, this is normal. This is what it's supposed to be. Excuse me. And this here, this 490, this is normal. This is what it's supposed to be. If you're ever scanning these and you see one of the three numbers in the phase different than the others, that should be an immediate concern because it means your building is having an electrical problem. And so just glance at these from time to time, get familiar with what some of these things are. And again, just if you are looking to understand your peak power demands for billing purposes, many times they're found mixed in the middle of all of this data. So with that in mind, blast through those over the course of a half hour. Hopefully you saw some value in that, but let me begin to summarize. And like I've done in the past, I wanted to give you some acronyms, another list. I know we had the webinar back in February, I think it was, where Sarah and I went through a bunch of acronyms in the industry, and these continue just to pop up all over the place. But regarding building automation systems, you see DDC and PLC. These are very common terms that are used. This idea of BACnet and Modbus and LODWorks, all of these are just part of the lingo. So do your homework on these and understand what these things are. Again, BACnet is I just want to remind you, it's the dominant open communication protocol. So all these systems, as they're communicating behind the scenes, many of them are using BACnet, but you'll hear the guys talk about Modbus and LODWorks. So just know, again, some of that lingo that's being tossed around. Other acronyms, FDD, so fault detection and diagnostics. So again, the idea of the system finding faults and bringing things to your attention so that you can solve problems. Recommissioning and commissioning these systems, again, so important. You've heard me say that many times in these webinars. And again, just energy conservation measure and measurement verification, all lingo, hopefully that it's becoming more and more familiar to you as I do these webinars. So last couple slides, just want to talk about the common failures, the things to look for. So out in the field, stuck actuators and dampers are always a challenge. So many times you learn these things by looking at the screens. You sit behind the building automation system and you see valves that are giving you inconsistent values or dampers that just don't seem to be closing properly because of temperatures. But very common phenomena of failure, failed or drifted sensors. So yeah, temperature is supposed to be reading 70, but the sensor's showing 67, so it's drifted by more than a couple degrees, so it's creating other problems downstream. Overrides, people overriding the system. These schedule drift, again, schedules, they just get stretched out because occupants keep coming and going, and rather than schedule it more consistent with how people occupy the space, people stretch it out. Mentioned this earlier about heating and cooling with a deadband. So heating and cooling occurring at the same temperature. You want to make it so systems have temperatures where it's not heating or cooling. And communication failures too happens with everybody. So just make sure you're checking your buildings consistently and identifying those sooner rather than later. Other things to look for is if a temperature is trying to if you're trying to find the right temperature in a space, sometimes it might be a little bit low or a little bit high. A term in the industry is called hunting. It's hunting for the right temperature. This idea of low delta T. So you don't have enough temperature change for your chiller and your boiler systems. I mentioned economizer lockouts, boilers and chillers that are short cycling, so they're turning on and off too quickly. And this is where I think you got to start. I think you got to start by checking your schedules, look for those overrides. Again, look for those dead bands. Make sure you're looking at those reset schedules. I had mentioned that earlier a couple times. Just the reset schedule is just so important to make sure that you're not overheating or overcooling or creating too much heat or cold unnecessarily. And just make sure you're verifying your sensors that they're calibrated in some type of regimen. Again, something that causes your system to not run properly if your sensors get out of calibration. Finally, I think this last slide that I've got is what we want to do is, I didn't mention this until now, but you want to make sure your outdoor air temperature sensor is working correctly and it's providing good data. Your outdoor air temperature sensor drives the decision for a lot of devices in your building. So boilers, chillers, air handling units may run or not run if it's sensing the wrong outside air temperature sensor. So make sure it's giving you an accurate reading. Make sure it's not in the sunshine. It's being protected. It doesn't get any type of false readings because that one simple sensor can have a wildly different effect in your building if it's not behaving properly. Check those damper positions that are right. Look for your economizers. Make sure those status points and command points are telling you the same story. Again, check the VFDs for reasonableness, those redundant pumping and the valve positions. And what I've got here is an image on the screen is what one of those MEP documents. I mentioned a couple times how you want to compare how your building is performing with the MEP documents. And this is an example of one if you haven't seen it. So it's a schematic of the building. There's tables, there's charts. This, once again, is the answer key for your building where all the numbers reside that you need to know. So find those MEP documents. And if you're unfamiliar with how to read them, get some help from somebody. But this is really where you need to spend some time if you really want to appreciate your building automation system. So Sarah, as I wrap up here, I don't know if we have any questions come in, but I just want to make sure people were aware of some upcoming webinars we have and find out if there was any questions.
Yeah, we do. We have a couple of questions. So one question was, how important are T and B studies to providing optimum BAS performance? I've heard T and B. I've also heard TAB. So assuming, Gary, who asked this question, assuming they're the same things, testing, adjustment, and balancing, or just
Yeah.
testing and balancing.
Yeah. So TAB, a lot of times called just TAB reports, the testing and balancing reports. How
Yep.
important are they? Sarah, they are one of those things that gets cut out many times at the end of a project because it's over budget. And so people run out of time and run out of money and then they don't never get it done. And it's one of the biggest leading causes of waste, in my opinion, in the whole industry is because it is critically important that systems are tested and balanced before they're released to be used. But as I've said, it's a major chink in the armor of the industry where people don't do it as well as they should.
Yeah, yep, agreed. Fair enough. And we also had a question. So earlier on, we had a comment from Chris about using schedules to avoid startup during peak time, the most costly time. And there was a follow-up question to that of how do you know, or is there a way to prove that you have a building that is starting up during that peak time, or basically when do you know when that peak time is that your utility's charging you the most?
Yeah, I think Sarah, it's tying things back to the bill, like understanding what the windows of time are, but it's also one of the things I wasn't able to share in the webinar today was some of the trending capabilities of a building automation system where you can begin to see load profiles or see how things change. My advice to the person asking the question is begin to understand better what your building automation system can and cannot do in terms of understanding what's going on in the buildings when you're not there. So virtually use the clues that are out there. but I'd also say is you have to go to some of these places at times too. I mean, in my job as an energy manager, many times I was up at 3 o'clock in the morning and I was walking through buildings at 4 o'clock in the morning because I really wanted to be there to experience what was going on. And so, can we do that every day? No, that's hard in our schedules to do, but periodically it's really important to get out in the field and check those things firsthand because it's just the information is just irreplaceable. I mean, it just really informs all of your decisions and really helps you better manage.
Well, that was it for major questions, Tom. Last thing I'll say, thanks to folks who are still with us. We've had an unusually high number of requests for the slides for this presentation. So, Tom, good job on that. Lots of useful content. So, we will make sure, yes, this is getting recorded. We had that asked a couple of times as well. It is getting recorded. That recording will be sent out to you. You can use it yourself, share it with others. We'll also make sure in this instance that the PDF of the slides go out as well. So you all can use some of the visuals that Tom has used here. And Tom, thank you very much, as always, for your expertise. Everyone, thanks very much for lots of engagements and questions. And please join us next time. And also check out Catalyst coming up this September. And we hope to see you all soon.
Awesome. Thanks, everybody. Have a great day.
Thanks, everyone.